Okay, so welcome to this video lecture. So we are going to have the topic mechanics of deformable bodies, or the simple string. So let me have our outcomes based learning objectives. So at the end of this module, you will be able to enumerate and describe different stages of material behavior and their gradual increase in loading, and then illustrate the geometry of elastic deformation on structures or structural member, and then discuss simple strain as a design parameter in design of structures, then choose appropriate structural material based on analysis and calculations. We also be able to evaluate behavior of engineering materials under temperature changes, and then state all engineering technical terms involved in simple strain. Then describe the material behavior under different types of stresses, and construct comprehensive free body diagram in solving problems, then relate to different formulas, variables, and units involved in simple strain, and finally interpret and discuss results of analysis of internal forces. Here we have a lot of learning objectives, since this chapter covers a lot of topics. So for the simple strain, as chapter 1, we have introduced the concept of stress as a fundamental engineering calculation. So here we have another useful analysis which determines the deformation or strain that is experienced in structural members or assemblies, while the term strain can loosely refer to processes, okay, and it is defined much more rigorously. So strain in construction materials can easily lead to distractions, okay, if applied stresses become larger than anticipated, or dead loads unexpectedly become live loads. So as an example, we can have the classic film of Tacoma Narrows Bridge collapse in 1940. So although designed to withstand winds up to 120 miles per hour, a relatively light wind of around 40 mph apparently set up a live, flatter oscillation not anticipated by the design parameters. So in short, it should be designed as 120. However, in the end, it has collapsed with only 40 miles per hour wind. So it becomes crucial. So we should have then to know that strain or deformation can be expected in a structure when worst case design loads are applied. So simple strain is also known as unit deformation, where it expresses the distribution of the deformation all over the length. So it is actually expressed by the formula below. So it is epsilon equal to deformation all over the original length. So let us correct the unit here, that the epsilon is unitless supposedly, because it is the quotient of the delta and the original length, wherein the unit will just be cancelled out. And the length could be in terms of meter, millimeter, feet, or inches. And then the delta will be in terms of millimeter, meter, or could be in inches or feet. as we can see here in the figure, this structural member was subjected to a deformation with the application of P. Therefore, P here will cause a stress on the member. And if it will cause a stress on the member, it will cause a strain, or the simple strain, or the unit deformation. That is why in the previous chapter, sigma is equal to P over A is what we call the unit load. And simple strain is the ratio of the deformational over the original length is what we call the unit deformation. So in short, simple stress is always paired to simple strain. So in every unit load, there must be a unit deformation. So there must be a conditions where the strain should be constant. First, the specimen must be of uniform cross-section. So if your member is a triangle, it must be the same triangle all throughout the length. It cannot be that from circular it will become an ellipse, or from ellipse it will become a shape of the rectangle. So in short, it must be consistent. It should have a consistent shape all throughout the length for the strain to be constant. And then second, the material must be homogeneous. So when we say homogeneous, there will be only a single material along the cross section. Cannot be that from 1 meter, from 0 to 1 meter, you have a steel, and then from that, there will be another material like bronze, and then there will be another material like aluminum. So in short, you cannot have a heterogeneous material if you wanted that the strain should be constant. So another criteria is that the load must be axial so as to produce uniform stress. So an axial load is a force that is parallel to the axis of the member. So it could be either a tensile or stretching, or compression, or compressing the material. Okay, so those are the conditions where strain should be constant. So we have here the relationship between stress and strain. So it is actually portrayed into this stress and strain diagram. This diagram is a result of a tensile test, okay, tensile test, where the material is gripped at both ends, and then a loading will be applied with a gradual increase, and then from that, unit load is then plotted. So we can see here, unit load is stress on the y-axis, while the unit deformation is on the x-axis or abscissa. Now, there are several stages on the stress-strain diagram wherein there are various behavior of the material. First, we have the proportional limit. So up to this amount of stress is proportional to strain. So the stress-strain graph is a straight line. Okay, and the gradient will be equal to the elastic modulus of the material wherein this is the Hooke's law actually. Okay, within this line, the stress is directly proportional to the strain. From the origin O to the point P is called the proportional limit. Again, the stress-strain curve is a straight line. This linear relation between the elongation and the actual force causing was first noticed by Sir Robert Hooke in the year 1678. Thus, it is called the Hooke's law, that within the proportional limit, the stress is directly proportional to strain. So therefore, from the origin of this P, or the proportional limit, the material will tend to go back to its original state when the load is released. The proportional limit is expressed in terms of the Young's modulus of elasticity. So the Young's modulus of elasticity is just the slope. It's just the slope of our proportional limit. What is the slope? Y over X, or rise all over run. And what is our y-axis? That is stress. And the x-axis is strain. Therefore, for the unit of that, if this is in megapascal and this is unitless, or millimeter per millimeter, Young's modulus of elasticity is simply equal to megapascal. So take note that we will be using this formula over and over again. And this is one of the criteria on problems in deformation. So that is the proportional limit. So next to that is the elastic limit. Beyond the elastic limit, permanent deformation will occur. The elastic limit is therefore the lowest stress point at which permanent deformation can be measured. This requires a manual load-unload procedure, and the accuracy is critically dependent on the equipment used and the operator skill. So for elastomers, examples are rubber. Okay, the elastic limit is much larger than the proportionality limit. Also, precise strain measurements have shown that plastic strain begins at very low stresses. So that is elastic limit. And then from that, if we increase the loading, it will reach the yield point, wherein the yield point is the point in the stress curve at which the curve levels off and plastic deformation begins to occur. This is point where there is an appreciable elongation without any increase in the loading. Hence, the load gradually decreases while yielding occurs. So there will be an appreciable deformation until it will reach the highest point, or the highest ordinate in the stress strain curve, wherein this is the ultimate strength. And if we gradually increase the loading, okay, from this point you can see here that the loading is actually decreasing, or it will tend to increase until the rupture strength. And the rupture strength, it is the stress at failure. Okay, it is the stress at failure. So here we have a comparison between brittle failure and the ductile failure. A ductile failure has a relatively large tensile strains, while that of brittle failure has a relatively small strain values up to the point of rupture. So examples of ductile engineering materials are structural steel and aluminum. For brittle engineering materials, examples are concrete and cast iron. So we can see in the figure the sudden failure of the brittle material. So there is a sharp breakage or brittle failure evident on the cross-section after rupture, while the ductile failure shows appreciable deformation here before the rupture. It is evident that the cross-section has undergone necking. So this is what we call necking. Okay, necking meaning the cross-section gradually decreases until it will rupture or the rupture will take place. So we also have here another property, modulus of resilience. This is actually the work done on the unit volume of material as the force is gradually increased from the point of origin. So this is the point of origin up to the proportional limit, and the unit is Newton meter per cubic meter. This may be calculated as the area under the stress strain curve from the point of origin up to the elastic limit E. So it is just the area bounded by the straight line, and the straight line is, as we all know, that is the proportional limit. And from that, we'll just have to project it down below the curve. So we will have a triangular shape here and compute that area. That will be the modulus of resilience. The resilience of the material is its ability to absorb energy without creating a permanent distortion. So next, moving on to modulus of toughness. So this is actually the work done on a unit volume of a material as the force is gradually increased from 0 to R. What is R? It is the rupture or the end point of our stress and strain diagram. So again, the same unit, we have Newton meter per cubic meter, and this may be calculated as the area under the entire stress strain curve from point of origin up to the point of rupture. And then the toughness of a material is its ability to absorb energy without causing it to break. So let me have here the working stress, allowable stress, and the factor of safety. So let me elaborate this by a simple figure here. So it actually takes off from the fundamental idea that capacity or strength S should always be greater than the applied load L. So as we can see here, factor of safety is the capacity of overloading. We do not want that the loading will exceed the capacity of the bridge here. So the capacity of the bridge on this figure is 30 tons, wherein the track passing is 25 tons. So therefore, there is a check mark, meaning we have a factor of safety 1.2. So from the word safety, then it implies that the structure is still on its within its functionality. While in this right figure here, the weight of track passing, which is 36 tons, exceeds the capacity of the bridge. Now, this has an X mark because the factor of safety is below 1, meaning it is indicative of failure. Okay? That is all about factor of safety. And as we can see here, the relationship between a factor of safety the stress at yield, and the allowable stress. So let me first define the working stress. It is defined as the actual stress of a material under a given loading. The maximum safe stress that a material can carry is termed as the allowable stress. The allowable stress should be limited to values not exceeding the proportional limit. However, since proportional limit is difficult to determine accurately, the allowable stress is taken as either the yield point or ultimate strength divided by a factor of safety. The ratio of this strength, or the ultimate or yield strength, to allowable strength is called the factor of safety. Hence, we can see here the formula. Factor of safety is equal to sigma y all over sigma allowable. So recall that the yield strength, after the yield strength, there will be an appreciable deformation. So we do not want that to happen. Therefore, sigma y should always be greater than that of the allowable. And as we all know that the allowable sigma here is being used in determining the appropriate area and the limit of our loading. So hence, the design criteria itself. So the design criteria itself is always less than that of the actual yield strength of the material. Hence, we can obtain a safety factor on this formula. And I think that ends our introduction for the simple strain. So let us have example. Please stand by for the example. Thank you for listening and good day.